So putting all this together, I just have some predict the product questions like what we would see on a typical exam, and we'll finish up after that. The first compound here has 3 leaving groups, all chlorides. We're adding sodium azide, which is actually a nucleophile from orgo-1, but a weak base. It's also in a polar aprotic solvent. So this is the recipe for SN2 chemistry. But you're being asked something about the selectivity because there's only one equivalent of this nucleophile. So we're being asked which leaving group leaves fastest. And all the leaving groups are the same. They're all chlorides. But the carbons they are on are not the same. These two are sp3 hybridized, while the vinyl one is sp2. And we know that sp2 cannot undergo SN2 chemistry, so that one's out. Both of the sp3s are secondary, so they're similarly hindered. One of them is allylic, or one away from an sp2. The other one is far from an sp2, it's alkyl. And remember from chapter 17 that allylics are very, very reactive. They're very fast to undergo SN1, E1, and E2. And that was explained in the video series, of course. There's a transition state model for showing why this undergoes substitutions quickly. It's due to conjugation. So the major product he's going to want you to draw here is where you keep the 2 chlorides intact at the vinylic and alkyl positions, and you substitute the allylic chloride from the back face, right, with the azide nucleophile, because we get stereochemical inversion upon SN2 chemistry. The azide attacks from the back face since the chloride was on the front. Okay. So that reaction really is nothing new. It's just explaining SN2 selectivity. Let's look at one that is now from chapter 18, where we have an Aryl chloride. So since this is not a withdrawing group, then we can't do addition and elimination followed to make the Mesenheimer intermediate. Instead, we have to do elimination addition. Of course, no SN2 is possible or SN1 because we have an aryl carbon with a leaving group. So the reagent set here includes a super base. This is really similar to NH2 minus. Right? We have a non-metal nitrogen anion next to a lithium cation. A very strong base with 2 lone pairs. So this is going to go through a benzyne intermediate. Now, there are 2 possible benzynes that could form because there are 2 unique hydrogens that could be eliminated. 2 of them are ortho to the chlorine. So when you form the benzyne, it could form here, in between the substituents, or one away from this vinyl group. Or you could form the benzyne with the other carbon up top, like this. I'm going to shift the pi bonds around so there's a triple bond there. You get 2 benzyne intermediates, both of which share this position that was chlorinated. The para position to the vinyl is part of the benzyne in the lower structure, and the ortho position to this vinyl group is part of the benzyne in the other structure. So now when the nucleophile attacks, I'm not going to show the whole mechanism because it's the same as the one above. But the nucleophile could attack here, or it could attack there. Likewise, for the other benzyne intermediate, it could attack meta or para. So this is the first example where we've made two different benzynes because there was no symmetry in the original compound. So eventually, after you do some proton transfers, you could get the meta product where the chlorine was. You can make the ortho product, or you could get para. And determining the major product here is you probably won't be responsible for doing that. You would just want to be able to draw all of these. Sterically, the para product is preferred, but statistically, the meta position, the purple carbon here, is actually the most likely one because purple carbon is part of the benzyne in both of these structures. So you would just pour those products, and that's proof that it goes through benzyne intermediates if you get those really three products, because these two are the same. There's no need to draw it twice. So just drawing these three is valid. Okay. The next one, we once again have Aryl halides, but now there's a carbonyl withdrawing group. That carbonyl is not conjugated or withdrawing from the benzene ring this way. Because this carbon right here is sp3. It doesn't have a p orbital to continue the conjugation. But it is conjugated through the alkene, actually, into the arene. This is the conjugated system. And just going through and marking the positive charge or thinking about the carbons that are being withdrawn from is the best way to do this problem. First of all, the carbonyl carbon is electron poor. And if you push electron density into the withdrawing, the next positive charge will land on this, what's called beta carbon. And that carbon, which is electron poor, is the effective electron withdrawing group that's directly attached to the benzene ring. And then the positive charge skips this carbon, goes to the next. Skips this carbon, next, and then it's here. It's at every other position. So if you think of this bond as being to the withdrawing group, this chloro is ortho. And this one's meta. So the only one that can be substituted for there via addition elimination is the chloro that's ortho. So if you want, you can draw out this mechanism, but the ethoxide would attack this carbon. Okay, that would push the electron density into the arene, which I'm going to push this way to get it onto the withdrawing group. So that would go through the Mesenheimer complex intermediate, where now there are 4 sigma bonds and sp3 hybridization at that ortho carbon. And the negative charge is on the electronegative atom, the oxygen. And then the last step is just to eliminate. Form the carbonyl, push the pi electrons back into the ring, to restore aromaticity. And I need to shift pi bonds around. They are right here and there. That reforms aromaticity and gives you the substitution product where the ethoxide is just in place of the chloro, only the one that was ortho to the withdrawing group. Okay, so that one's a little tricky because the withdrawing group is sort of hidden. So it's oftentimes best to draw all that partial positive charge at every other position, starting with the withdrawing group, to figure out which carbon is electrophilic if you're not sure what's withdrawing or what's ortho versus meta versus para. All right, the last thing we'll do here is an additional NAS, where we have a very strong withdrawing group, nitro, and we add a nucleophile. And that nucleophile is going to substitute only for the fluoro that's paired, the meta one. So it will become OH in replacement of the parafluoro, and the other fluoro and nitro remain. Now, this phenol, once again, is acidic. It's on an electronegative atom. This proton can be easily deprotonated. It's also para to an electron withdrawing group. So with extra hydroxide in solution, as we'll learn in this chapter, that can be deprotonated to give an anion. So when you have a phenol in basic solution, you really get the phenolate ion, which is also a nucleophile. And that oxygen nucleophile is now being treated with a halide electrophile, where one carbon is vinyl, an sp2, but the other one is aliphatic or singly bound, an sp3. So a good nucleophile like phenolate can undergo an SN2 reaction, an sp3 hybrid that has a good leaving group. So it attacks and kicks off the bromide. So connecting the structure, we have a new CO bond, and then the vinyl bromide goes untouched through SN2. Okay. The last part of this is now incorporating some 16, because these arenes also undergo EAS chemistry with reagents like chlorine, bromine, in the presence of a Lewis acid, ferric chloride. Now, EAS is sort of a throwback at this point compared to NAS. During EAS, nothing happens to this leaving group, but instead we're going to substitute an aryl hydrogen with a chlorine. So now the benzene ring is the nucleophile, and it's nucleophilic because it has this oxygen that's a pi electron donating group, or it's donating into the ring. Remember that electron donating groups are ortho-para directors. The nitro is electron withdrawing, which causes it to be a meta director. This meta position is taken, but this one here has a hydrogen. That's meta to the nitro, and it's also ortho to the methoxy. So they agree on electrophilic aromatic substitution for this position. So those EAS reactions can be thrown in synthesis along with the NAS reactions now. So that becomes chloro. Fluoro remains unchanged. So does the ether. And the nitro remains unchanged. So that's via EAS.